If you have studied any physics other than quantum mechanics, you would know relation between particle properties, for example, between linear momentum and velocity, or between energy and momentum, or you know relation between wave quantities and wave quantities like angular frequency or frequency and wavelengths, both are wave quantities, and so on. And this applies to even Einstein's general relativity or special relativity. But in quantum mechanics, you have something special, and that is part of wave particle duality, and that is that you have wave quantities and particle quantities proportional to each other. They are related to each other. And so that is wave particle duality, and the first job of this lecture is to complete any description of wave particle duality in a quantitatively clear and workable way. And what I mean to say is there is a clear, well-defined role of wave quantities, and that is that our mathematics of travel of wave when we are not detecting it, that depends upon wave quantities like angular frequency or wavelength, or when a wave strikes and you have a dots and detection and you have a large number of detections, then the pattern properties are dependent on wave quantities. So these are roles of wave quantities, and there is a similar or different role of particle quantities, and that is the individual dots properties are determined by particle properties. So that is one job of this lecture, and then is that the relation, then is a bit of history where you can say the relation between wave and particle quantities energy, and wave quantities frequency, that was told for photons, especially photoelectric effect, by Einstein. And de Broglie suggested that that should be valid for every particle, not only photon but electron as well. And that is the history, and related to that is an important thing is that this new proposal in 1924 helped understanding Bohr's quantization, Bohr model, as a part of something like a general principle, which in 2 years' time became a general comprehensive theory, namely quantum mechanics. Before that, Bohr's principle was a model only limited to only one particular problem. So that's that's essential to know for knowing what is the importance of D. Now at that moment I should talk about the pronunciation of D. Broglie. Actually the French pronunciation is Dubois. So in English, nearest you can say De Broglie, and that I will use it. Okay, now the thing is, what was De Broglie's suggestion? That was about one wave, sometime interpreted as one electron is a wave, and photon is a wave, and sometimes interpreted as electron has an associated wave. But I should tell you that exactly, if you think of that way, the situation is slightly different in quantum mechanics. In quantum mechanics, a particle is not a wave associated, not A. A particle is a wave packet, and wave packet has many waves, and many waves means many momenta in a single particle. So that's the difference between the De Broglie principle and quantum mechanics that is to be conveyed. So that's the full scheme. Now come to details of that. First is, as I told you, the role of wave properties and particle properties. And as I told you, when the particle is traveling, and that may be electron, that may be photon, whatever it is. When it's traveling, and we have to describe this mathematics, we use plane waves or linear combination of plane wave. The mathematics of plane wave is e by iota kx minus omega t. And for example, is omega, this appears, that's angular frequency. Now frequency is vibration per second, and one vibration is in one circle. You have 2 pi radians. So one vibration per second means 2 pi radians per second, and that is angular frequency. And next onward, I will not use frequency, I will use angular frequency, and you will have to remember that lesson. So that's the one role of wave quantities, namely at this moment I'm talking about frequencies. Another role is that when its effects are seen in a large number of dots, this pattern is a wave pattern, and the wave pattern is dependent on wave properties. It is related to omega, whatever is wave quantity. And then where the wave? And the answer is, where is the particle? And the answer is that if you describe properties of a single dot, then one dot appeared, how much was the energy transferred, and how much the electric charge transferred, and so on. Remember, that energy and that electric charge is not separatable. There is no half of that, there is no quarter of that, there is no third of that. Although there can be, probability wave can have half or quarter, but not the particle. The dot is a particle. That is the energy, that's no half of it. Now energy is related to, Einstein said that energy, the particle quantity, is related to frequency, which is wave property. Another thing in Einstein's work has been a relation between this particle property, energy, to another particle property, which is momentum. Now this equation, I don't have time to describe it because this is not a course on relativity. Otherwise, this is just a 4 or 5 lines that we moving mass formula, m is equal to m naught divided by 1 minus v square over c square under root. You square it and you use e is equal to mc square and things like that, and you arrive at that. And for photon, m naught is 0, so you get e is equal to pc. You combine these, left hand side is the same, so right hand side you equate them, and you divide both sides by c. You have hf divided by c, and frequency over speed is reciprocal of wavelength. So here you have an equation. Remember, that is by an Einstein work, it is an equation for a photon, and that is wave, and everyone thought for photon has a wavelength, but de Broglie suggested that the same equation can be used for electron as well, and no one even thought at that moment that electron would have wavelength, but he said no, still use it. So that's if you use it, then in wave properties you have wavelength added as well. So far it was only frequency, but the same thing applies to that. This travel is described by wavelength or reciprocal of wavelength. It appears in this course in form of wave number. K has already appeared as a kx in plane wave. Now if you want to know the relation between this newly suggested quantity wavelength and old quantity which has appeared in this course so far is a k, the relation is that if you take a full repetition, you have an angle is 2 pi radians, and kx changes, here's the angle, this is a phase. So when angle changes by 2 pi, this part changes by k, and x becomes lambda, full wavelength. So that is kx becomes k lambda is equal to 2 pi, and that gives you that relation. So now next onward you have to remember k rather than wavelength. So now I'm just kind of repeating that travel and pattern is described by wave quantities, and in their wave quantities now you add this k as well. So now the next question is that what is the logical status of what we studied so far here. Einstein said it's only for S mass 0. Is it generalizable? If we change rest mass to non-zero, will we have to change equation? You see the face on the face of it, this equation does not mention m naught. So if you say this is valid for non-zero m naught as well, one thing is noticeable, that equation will not change. So that means there can be room for generalization. But should we generalize? De Broglie said, yes, generalize it. And he used it. Was it a clash with Einstein? It was a blunder, or it was a generalization? Generalization means that Einstein had discovered it for a special case, m naught is equal to 0, and the general equation is that, and Einstein had a special case of it. So what was that? Was it blunder, a mistake, misunderstanding Einstein, or generalization? Related to that, you should know two things. One was the experiment 1923-27, which showed that in experiment there is a current, and in modern terminology, in modern understanding, I would say these electrons are traveling. And I told you, here, when it is traveling, it's a wave. So when it was traveling, it was a wave. And the result here, at this Davidson experiment, you remember it's in 1923-27. The experiment which I showed you here, that was done something like 50 years later. So in this later 70s or 80s experiment, it was possible to see individual dots. But if you go back in history, 50 years ago, it wasn't possible to see individual dots. What you could see was only the pattern, that thing, and that was seen in Davidson experiment in just in a wave-like pattern. So that shows, you can say, wave nature. I would say wave role, of traveling wave role and detectant wave role, but normally it's called wave nature of electron. And the question maybe is that why was this experiment performed? What was the importance of this idea? Why it was considered worth an experiment? And maybe historically it was that. But anyway, that's a part of science. You should know that in any case, whether it was actually history or not. But it could be in any possible next time history. When you give a new idea, you should show some worth of it, even if possible. You should show worth even without spending money on a new experiment. And it was possible in case of De Broglie, that he could show that an already experimental knowledge in the form of Bohr atomic model could be explained, could be incorporated in a general principle through De Broglie's idea. The detail is the following. That to understand that topic, this is history, but meanwhile, as a side effect, you should also learn something, which is that so far, if you see actual content, what I've been telling you so far is a wave mechanics, not quantum mechanics. Literally, because the wave has appeared again and again. The quantum means discretization. The word quantum. Where is discretization? So far, in the whole description, there has never been discretization. Discretization appears now, actually. And that is that if you have a standing wave, then is a discretization in this way. You have a standing wave and you require that it is the same amplitude at 0 and length L, then you can fit only an integer, one wavelength or two wavelengths or three wavelengths and so on, not any fraction of any wavelength. So that means this L, in L you can fit in only an integer number of wavelengths. An integer is discretization, and that is a quantization. And one thing is history, and if you are interested in future, means here the future means maybe in the next lecture, you have to remember not every wave is quantized, only standing waves are quantized. So if the wave is not quantized, it would be historically called quantum mechanics, but actually it may not be quantum if the wave is not standing. So that is whatever is historically what you interpret, but that lesson you should remember. Anyway, I complete that history, that now De Broglie applied that to electron. And remember, here it was something, you have a string vibrating or so. Electron, is that electron something or so? Can we know what is what is electron? What is the L for electron? You remember, you need not answer that. You need not know what electron is. What is, because if you know that why physicists can make statements about and workable, scientific, testable statements about electrons and atoms and electrons, and even for smaller particle or so, we can see them. It's not because of microscope that we know. What we know this particle is because one thing we know. We don't know what the material is. We don't know what kind of wave it is. But we know mathematics applies there as well. And in mathematics, if you have a circle, no matter, you don't need to know what kind of circle it is. What is the electron wave? What is the property? No, it's a mathematics. If a circle, and if you take one complete circumference, then everything, every quantity becomes same because it's the same angle, so same property. So when this thing is here, it repeats after L. But a circle, when circumference is completed, it's the same point, so everything is repeated. So this means L is replaced with the circumference 2 pi r. Now that's a formula you have as a mathematical property of a circle, and you combine this with the Broglie equation. You take wavelength from that and you put in here and you rearrange it slightly, you get that. And do you recognize what is PR and what was Bohr? I just remind you, hopefully it's a simple thing, that angular momentum is r cross p, magnitude is rp sine theta. Theta is the angle between r and p is 90 degrees, sine 90 is 1, L is equal to PR, PR is L is equal to N, H over 2 pi. That's Bohr quantization. So I hope that speaks for itself. The success did speak, and that's why it became, anyway, it became part of modern quantum mechanics in 2 years' time, anyway, 1 or 2 years' time. Now, this is what became quantum mechanics 2 years' time, modern quantum mechanics. It's the same as the Broglie relation. The answer is somewhat but not exact, because de Broglie is talking about one wavelength. Maybe said that electron is a wavelength, or there's one wave associated with electron. But modern quantum mechanics, we don't have one wave. We have a photon, namely photon, electron, or whatever the particle is a wave packet. And packet means is a packet of many waves, and many means many values of this variable k. You remember, that's related to wavelength. Many waves means many wavelengths, many k's, and there are many. There's not one. That's the difference between de Broglie and full-fledged quantum mechanics. And there are many waves, many wavelengths, and many momenta as well. And de Broglie would have said maybe one momentum, but not one. Quantum mechanics has many momentum. Now, to conclude that in this lecture what we have done is I've completed description of wave-particle duality, and I hope it was clearly stated, workable, clear role of wave and properties, not left to things like that, sometime wave, sometime particle, depends upon experiment, nothing like that. It's a clear role. Every experiment, if you are talking about travel and large number of detection, the pattern, it's a wave, and if it's a single particle, it's a single detection, it's a particle. Simple, not dependent upon experiment. Another thing is that the wave and particle quantities are related. For a photon, these were related by Einstein, and de Broglie generalized it to every particle. At that moment, the first application was electron in Bohr atom, and the success has been conveyed to you. That would have given importance to this de Broglie idea. And the last thing is it quantum mechanics? The answer is not quite, because quantum mechanics has not one wavelength, has many wavelengths, and many wavelengths mean many momenta, and one particle has many momenta. Yes, that's quantum mechanics says. But remember, it's not one the momenta, they are possible momentum. The quantum mechanics is everything, there are waves, but everything is a probability wave. So the probabilities of possibilities. So the many momentum are possible when you open that packet. When you measure, one of the momenta will appear. So that means which one will appear, which momentum will appear. That's uncertainty, and that's Heisenberg's uncertainty principle. That's the next topic, and to know when the next topic is taught, you must subscribe to this channel so that next I can tell you what is Heisenberg uncertainty principle. So please subscribe and wait for the uploading.